to strictly typed languages like C++ or Python, JavaScript has a reputation in the industry for being erratic. It is often described as a chaotic, illogical system where the rules of mathematics and data seem to bend at random. Take this classic anomaly. If you subtract the number 2 from a string containing the character 5, the engine correctly processes the math and outputs the number 3. But if you change that minus to a plus, the math stops. Adding a number to a string yields a concatenated text string of 52. And then there is the ultimate logical contradiction. You can ask the language if an empty array is loosely equal to the number 0, and it will confidently tell you that is true. When developers encounter these outputs, the instinct is to write them off as engine bugs. They assume the language is just flawed. But JavaScript is actually a highly literal machine. It is governed by strict ECMAScript specifications. What appear to be random quirks are actually entirely predictable execution algorithms firing exactly as designed. Mastering JavaScript requires abandoning the idea that the engine uses magic. You have to map the precise logic gates of its memory and execution contexts. The mechanism behind those strange math equations is called type coercion. This is the engine's internal process of converting one data type into another to successfully complete an operation. Sometimes this is explicit. You intentionally write a command to convert a number to a string. But usually it is implicit. The engine forces the conversion in the background without telling you. This flowchart represents the JavaScript interpreter handling the plus operator. When the equation 5 plus the string 2 enters the system, the plus gate flashes. The engine detects a type mismatch. The rule here is strict. If either operand is a string, the plus operator will always abandon math and default to concatenation. It forces the number 5 into a string and combines them. But watch the routing change for the minus, multiply, or divide operators. When a string and a number pass through the minus gate, the engine forces the string into a number type, outputting 3. These specific mathematical operators force a number coercion because the engine assumes your intent is calculation. It bends the data to fit the mathematical tool you selected. This same rigid logic applies to Boolean coercion. When JavaScript evaluates a value that isn't strictly true or false, like an object or a string, it categorizes it as either truthy or falsy. This grid shows the specific list of universally falsy values in JavaScript. If a value is not one of these exact 7 items, the engine will coerce it into a true Boolean. Now we can resolve the empty array equation. This step-by-step diagram shows how the loose equality operator triggers extreme implicit coercion. The engine converts the empty array into an empty string. Then, to compare it with a number, it forces that empty string into the number 0. 0 equals 0, so the engine returns true. An empty data structure mathematically equals 0 because the engine's internal logic prioritizes matching data types over preserving the structural logic of the array. Professional developers bypass this entirely. They use the strict equality operator, represented by 3 equal signs. Strict equality checks both the value and the data type simultaneously. If the types don't match exactly on the first check, it immediately returns false. No coercion allowed. Implicit coercion is the engine aggressively attempting to keep your program running. It guesses your intent so it doesn't crash. Understanding how the engine converts data naturally leads to how it physically stores that data in memory. Look at this split-screen memory map. On the left, we have primitive data types, like numbers, strings, and booleans. They are passed strictly by value. When you declare x equals 1 and then y equals x, the engine allocates 2 completely separate independent blocks. If you modify the y variable later, it has absolutely 0 effect on x. Their memory spaces are permanently isolated. On the right side, we see reference behavior. When you create a complex structure like a student object, the engine does not store the data inside the variable. It draws a pointer line from the variable to a distinct address block on the memory heap. Variables holding objects or arrays are empty of data. They act as directional pointers to a physical location. If you attempt to copy that object to a temporary variable, the engine does not duplicate the data. It simply draws a second pointer line from the new variable to the exact same memory address. This creates a state mutation trap. Altering a property on the temporary copy directly overwrites the data in the original shared memory space. This shared reference behavior causes massive cascading bugs. A minor update in one component silently corrupts data read by the rest of the application. To decouple the memory, engineers use the spread operator. By spreading the original object into a new structure, the copy pointer instantly detaches from the shared space and connects to a brand new memory address. The spread syntax explicitly forces the engine to allocate a distinct, independent block of memory, duplicating the data safely. Managing state immutably requires this deliberate severing of references. You have to tell the engine exactly when to share memory and when to isolate it. Preventing data corruption in JavaScript requires you to look past the variable names on the screen and control the invisible memory pointers connecting them. In full-stack development, you are constantly pulling external data payloads from APIs or the DOM. That data is frequently incomplete or entirely unpredictable. This diagram illustrates a script attempting to read a nested property in an incomplete JSON payload. The execution line traces down the tree, searching for an age value, but hits a null node at the profile level. The system crashes. Attempting to read a property of undefined triggers a fatal runtime error. The execution context shatters and the entire application stops functioning. To defend against this, modern syntax includes optional chaining. By appending a question mark to the execution path, optional chaining safely short-circuits the operation. If a node doesn't exist, it stops immediately, returning undefined instead of crashing the system. But returning undefined often leaves a blank spot in the user interface. That is resolved by its logical partner, nullish coalescing. By adding a double question mark, nullish coalescing injects a predefined fallback. If the execution line resolves to null or undefined, it routes the data through the coalescing gate and outputs a safe 0, or whatever default you choose. In legacy codebases, checking for missing data required writing multiple verbose if-else statements to manually catch every possible failure point. These modern operators are structural armor. They are designed to tightly guard your execution context from the unpredictable realities of external data. This unified schematic maps the mechanisms we've explored: the coercion flowcharts, the reference pointers mapping the memory heap, and the short-circuit failsafes. They reveal a single design paradigm. JavaScript is a heavily governed system that fiercely prioritizes execution continuity over strict typing constraints. Implicit coercion exists because the engine prefers to guess your intent rather than halt the program. Reference pointers exist because sharing memory addresses prevents massive data duplication, saving valuable system resources. And defensive syntax exists to guard those highly flexible structures against sudden runtime collapse. A coder fights the language's quirks, trying to force it to behave like C++. An engineer anticipates the engine's built-in behaviors and writes logic that aligns with them. Professional JavaScript engineering is the practice of strictly controlling memory references and explicitly guarding data. You take a seemingly chaotic environment and you run it as the precise, literal machine